The universe has long captivated us with its immense scales of distance and time. How far does it stretch? Where does it end? And what lies beyond its star fields? And streams of galaxies extending as far as telescopes can see. These questions are beginning to yield to a series of extraordinary new lines of investigation and technologies that are letting us peer into the most distant realms of the cosmos. But also at the behavior of matter and energy on the smallest of scales. Remarkably, our growing understanding of this kingdom of the ultra-tiny, inside the nuclei of atoms, permits us to glimpse the largest vistas of space and time. In ancient times, most observers saw the stars as a sphere surrounding the Earth, often the home of deities. The Greeks were first to see celestial events as phenomena, subject to human investigation, rather than the fickle whims of gods. One sky watcher, for example, suggested that meteors are made of materials found on Earth, and might even have come from the Earth. Those early astronomers built the foundations of modern science, but they would be shocked to see discoveries made by their contemporary counterparts. The stars and planets that once harbored the gods are now seen as but an infinitesimal part of a vast scaffold of matter and energy extending far out into space. Just how far began to emerge in the 1920s. Working at the huge new 100-inch Hooker telescope on California's Mount Wilson, astronomer Edwin Hubble and his assistant Milt Humason analyzed the light of fuzzy patches of sky, then known as nebulae. They showed that these were actually distant galaxies far beyond our own. Hubble and Humason discovered that most of them are moving away from us. The farther out they looked, the faster they were receding. This fact, now known as Hubble's law, suggests that there must have been a time when the matter in all of these galaxies was together in one place. That time, when our universe apparently sprung forth, has come to be called the Big Bang. How large the cosmos has gotten since then would depend on how long it's been growing and how fast it's been expanding. Recent precision measurements gathered by the Hubble Space Telescope and other instruments have brought a consensus that the universe dates back 13.7 billion years. The radius of the visible universe, then, is the distance a beam of light would have traveled in that time. 13.7 billion light years. But in fact, it's bigger, much bigger. How it got so large, so fast, was until recently a deep mystery. That the universe could expand had been predicted back in 1917 by Albert Einstein, except that Einstein himself didn't believe it until he saw Hubble and Humason's evidence. Einstein's general theory of relativity suggested that galaxies could be moving apart because space itself is expanding. So when a photon gets blasted out from a distant star, it moves through a cosmic landscape that is getting larger and larger, increasing the distance it must travel to reach us. The orbiting telescope named for Edwin Hubble began to take the measure of the universe by looking for the most distant galaxies it could see, pointing to our north, and then our south. Taking the expansion of the universe into account, the Space Telescope found galaxies that are now almost 46 billion light-years away from us in either direction, almost 92 billion light-years from one another. and that would be the whole universe, according to a straightforward model of the Big Bang. But remarkably, that might be a mere speck within the universe as a whole, according to a dramatic new theory that describes the origins of the cosmos. It is based on the discovery that energy is constantly welling up from the vacuum of space in the form of particles of opposite charge, matter and antimatter. Back in the 1980s, the physicist Alan Guth proposed that energy fields embedded in the vacuum of space suddenly tipped into a higher energy state, causing space and time to literally inflate. To go from atomic size to cosmological size within an infinitesimally short time. As a result, according to one calculation, the whole universe would have grown to some 10 billion trillion times the size of the observable universe. That's 10 followed by 24 zeros. Put another way, the complete universe is to the observable universe as the observable universe is to an atom. The fury of this period of cosmic inflation helps explain the immense size and relative smoothness of the universe. But to succeed, the theory must also account for how the universe produced what we see around us. All those stars and galaxies and clusters of galaxies, and ultimately, us. Scientists are now seeking to piece together the chain of events that launched our universe in its earliest moments, by generating what you might call a little bang. At the Brookhaven National Lab in New York State, there are blasting gold atoms in opposite directions down tunnels almost 2.5 miles long. When these atoms reach velocities just short of the speed of light, they are sent into a violent collision. A fireball erupts, reaching a temperature exceeding 2 trillion degrees centigrade. As far as we know, the last time anything in our universe was that hot was about 1/1,000,000th of a second after the universe was born. What interests the scientists is the splatter of subatomic particles, a super hot soup of quarks and gluons, particles that probably gave rise to matter as we know it. In initial tests, this quark-gluon plasma has shown a crucial property: extremely low viscosity, that's the resistance to flow. To grasp its importance, we go back to those primordial energy fields that the theory says spawned the Big Bang. The thinking is that those fields contained tiny fluctuations that were blown up to huge size during inflation. In the ultra-dense quark-gluon mix, these fluctuations generated pressure waves, or ripples. As the universe evolved, these ripples led to variations in the density of matter. Amazingly, the imprint of those ripples is out there today, first seen in a faint signal discovered accidentally in the 1960s. Working for the Bell Telephone Company, physicists Arno Penzias and Robert Wilson had built a giant horn-shaped antenna. But wherever they pointed it, the contraption picked up excessive noise in the microwave portion of the electromagnetic spectrum. That noise turned out to match a prediction made years earlier. That in the wake of the Big Bang, the universe was filled with a cloud of extremely hot gas that scattered all light. As the universe cooled, that cloud dissipated. Light then shone through. Over time, it shifted, as the universe expanded and cooled, to just the band of noise detected by Penzias and Wilson. What they'd heard was the echo of the Big Bang. This image shows the smooth contours of the light recorded by the Bell team. But scientists would have to look much closer to find the imprint of cosmic inflation. The space Space Shuttle Discovery lifted the Hubble Space Telescope into orbit on April 24, 1990, in one of the most important scientific milestones of our time. But another launch, arguably just as important, had taken place 5 months earlier. This was the Cosmic Observation Background Explorer, COBE for short. It was sent up to take a harder look at the microwave radiation discovered by Penzias and Wilson. The results came out 2.5 years later. The early universe contained a pattern of hot and cold spots. One COBE scientist called it the Fingerprint of Creation, for it showed the origin of the universe that we see around us today. Smooth on a large scale, but with significant clumps, from which gravity would have formed gas clouds, then stars, then galaxies. With this cosmic template in hand, astronomers set out to discover how these structures had evolved over time. In an age of computer-controlled telescopes and automated observing, astronomers could now launch complex international collaborations with the goal of mapping a large fraction of the universe in 3 dimensions. At Apache Point in New Mexico, the Sloan Digital Sky Survey set the standard for mass production astronomy. A series of steel plates are drilled with holes that exactly match the locations of galaxies in the night sky. After plugging fiber optic sensors into the holes, the plates capture the light of hundreds of galaxies per night, and that light determines their distances from the Earth. Another survey is named the 2-micron all-sky survey, or 2MASS, after the frequency of infrared light its detectors are tuned to capture. Here, these data go out to a region 60 million light-years across. This is our neighborhood. Jump further out to a region about 200 million light-years across. Our galactic neighborhood merges into the densely packed Virgo supercluster, which is the nearest intergalactic city. Stepping out to a region over 320 million light-years across, galaxies line up in walls and arcs that bound an array of sparsely populated voids, the rural cosmic countryside. Moving out with the data, this region is over 650 million light-years across. And finally, out to a region 6.5 billion light-years from end to end, the cosmic continent. In the middle of it all, our galaxy, so immense from our earthly perspective, is less than a speck. The 2MASS study, the Sloan Digital Sky Survey, and the 2-degree field in Australia have extended our maps to a quarter of the way back to the beginning of the universe. They've laid out a grand cosmic roadmap and gravitational routes. Now, COBE's successor, the Wilkinson Microwave Anisotropy Probe, or WMAP, was ready to scan the early universe for the fine-scale origins of this cosmic atlas. WMAP was launched far beyond any interference from Earth to a position balanced between the Earth and the Sun. There, for 2 years, its detectors took in the pristine light of deep space. This is what WMAP saw. A pattern consistent with the filaments and voids that had evolved in the universe at large, and with the tiny scale structures sketched by inflation at the very birth of the cosmos. Researchers at Brookhaven National Lab in the US and the new Large Hadron Collider in Europe will be probing ultra-high energy collisions in the coming years to tease out more details of the early universe. One group looked for repeating patterns that could be evidence of pressure waves that might have ricocheted through the hot gas of early times. But they saw none, which implies the universe had grown so large during inflation that waves could not cross it. Then they did the math. The entire universe has a minimum diameter of 156 billion light-years. Not quite twice the size of everything out there that we can see, the observable universe. What is its maximum size? And what's beyond that? We may never know for sure what lies over our visual horizon. But astronomers are turning up some surprising hints in the cosmos they can see. To ancient observers, the universe was made of 5 classical elements: earth, water, air, fire, and a 5th, quintessence, or space. The philosopher Aristotle believed the stars, unchanging and incorruptible, were made of this 5th element. Today, we're finding that space, in fact, has a character all its own. Astrophysicists have calculated the gravitational pull needed to bind stars as they orbit a galaxy, or galaxies as they orbit a cluster of galaxies. And they've found that there is simply nowhere near enough visible matter out there to hold these structures together. The missing ingredient, its identity still unknown, they call dark matter. In supercomputer simulations of cosmic evolution, dark matter is added in to supply the gravitational tug needed to form the web of filaments and walls, voids, and dense clusters we see in the universe at large. But something else appears to be happening on these large scales. Astronomers have been making refined measurements of the cosmic expansion rate with a new type of distance marker. And they wanted to know if gravity was slowing down the pace at which the universe is spreading out. But what they found comes as a shock. The markers they used, Type 1a supernovae, are thought to burn at uniform intensities throughout the universe. By measuring changes in the brightness of these so-called standard candles at various distances, the researchers have been hunting for changes in the rate at which the cosmos is expanding. They have shown that while local regions of the universe are drawing together, the universe as a whole is not only expanding, it's accelerating outward. The culprit is thought to be energy welling up from the vacuum of space, similar to what occurred in the early moments of the Big Bang, causing cosmic inflation. Now it's happening in minute quantities across vast regions. Over time, this so-called dark energy has grown to an astonishing 3/4 of all the matter and energy in the universe. With data like these pointing to an underlying dynamic within our universe, some scientists have suggested it's part of an even larger cosmic dynamic, much broader and deeper than we've ever thought. There is a version of inflationary theory that suggests we live in one of many universes, coexisting side by side, but out of touch with one another. Like bubbles, they are continually rising up and expanding across the oceans of infinity. Just 500 years ago, many people looked out into space and saw a universe of lights, small and nearby, centered on the Earth. The birth of astronomy revealed stars far from our planet, then galaxies, clusters of galaxies, and vast walls and filaments of matter. Our newest ideas about the size of the universe amount to a quantum leap in our sense of scale by extending these structures far, far beyond the horizon we can observe. Do these discoveries push us, on our tiny, out-of-the-way planet, into a smaller and smaller corner of the cosmos? Or does our ability to comprehend and imagine the far limits of time and space expand our importance in the grand scheme of things?